Hi everyone. This is the course EC657A, and the course instructor is Professor Mark Crowley. I am Benyamin Ghojogh, the TA and presenter of the slides. And this lecture is independent component analysis using singular value decomposition, or SVD. So first of all, I should say that independent component analysis can be done using different algorithms. One of them is maximum likelihood estimation, one of them is singular value decomposition. This lecture focuses on ICA, or independent component analysis, using SVD, or singular value decomposition. First, we talk about cocktail party effect and blind source separation. What is cocktail party effect? Assume that you are in a cocktail party and there are groups of people who are talking to each other. As you can see, there's so many voices that are around, and it's hard to say that which voice comes from which group. Assume that, for simplicity, assume that you only have two groups of people who are talking, and their tone of speaking, or what they are talking about, everything is different. So they are not completely similar voices. They are not completely correlated, but they are mixed. These voices are mixed. So you have two sources, S1 and S2, and assume that we are recording these voices in the party with two microphones, X1 and X2. So X1 and X2 are the measurements which measure the voices in the party, and S1 and S2 are the sources which generate the voices. What ICA wants to do, ICA wants to find the independent components of these voices in order to separate these sources for the sake of source separation, or blind source separation. And the thing is that it's a very hard task, because the voices are combined, and independent component analysis tries to separate these, and for example, then you can play the voice of each group separately, and you can easily hear what they are talking about. Now let's go into the mathematics notations of ICA. Assume we have two sources, as we discussed later. This is sooner. Two sources, S1 and S2. So we have two measurements or sensors, X1 and X2. We assume that each measurement is a linear combination of the sources, because usually this happens in nature. So if we have a linear combination, each measurement of each microphone is a linear combination of S1 and S2. This must be X2. X2 is also a linear combination of S1 and S2. Then if X1 is, so we can represent this the weights of linear combination by A11, A12, A21, and A22. If we might have image data rather than sound data. If X1 and X2 are images, then we should reshape them to column vectors. S1 and S2 are also vectors. They can be scalars too, but in general they are vectors. We can concatenate X1 and X2, or put them together in a vector X. Also put S1 and S2 together in a vector S. So we have a vector X of vector of measurements and vector of S or sources. Then in matrix form, this can be written as this. X is a matrix A11, A12, A21, A22, S, and we name this matrix capital A, and it's called mixing matrix. It's called mixing matrix A. Now this is mixing matrix. Let's go and say we have some assumptions. So first of all, I should say that in this equation 4, as you can see, the only thing that we know is x. Because we have the measurements of microphones, but we don't know a, the mixing components, and we don't know the sources. What we finally want to know is the sources, but we also don't know the weights of linear combination, and that makes the problem harder. So we have some assumptions in ICA. First, we center the measurements x1 and x2. We do that in PCA too, if you remember. We center for the sake of simplicity of computations. And we also assume that sources S1 and S2 are not Gaussian distributions, not Gaussian. Usually natural images and data are not Gaussian. So this assumption is valid. And why do we make this assumption? We will see later. Also, one small thing that I can tell you is that there is another reason that I will tell later, but one reason that they shouldn't be Gaussian, assume that this is Gaussian, a Gaussian distribution. Then you don't know whether this, for example, is the correct components or this is the correct components. Both can be valid, so it confuses the algorithm. This is one reason. And we assume that the sources are statistically independent. So we denote it by this. As they are statistically independent, we can write their joint distribution as the multiplication of their marginal distributions. Now let's talk about singular value decomposition for the sake of ICA. Recall that we had this. The measurements were the linear combination of the sources. Both A and S are unknown. Only X is known. Yes? Okay. Now let us apply SVD or singular value decomposition on matrix A, as we have in equation 5. So U here is the matrix of left singular vectors. V is the matrix of right singular vectors. Sigma is the diagonal matrix of singular values. We had X equals AS. Replace the singular value decomposition of A in this equation. We will have this. X equals U sigma V transpose S. Now, you might say, okay, if you can say this. S can be approximately, we can say estimated by this hat means estimation of S. A inverse X, am I right? So we are doing this here too. And then we can say that A was this, U sigma V transpose. So I replace this here. And now when we apply inverse to a multiplication of several matrices, their order is reversed. So we'll have V transpose inverse, sigma inverse, U inverse X. As in singular value decomposition, U and V are orthogonal matrices. Therefore, according to the definition of orthogonal matrix, U transpose is U inverse. Also, V transpose is V inverse. Therefore, as V transpose is V inverse, this is V inverse inverse, so becomes V. Here we have it. Sigma inverse, we still have it here, and U inverse will replace it by U transpose. So V sigma inverse U transpose, and then we'll have X. So what we had here, we had singular value decomposition on A, and then S, the estimation of S, the sources. We wanted, do you remember, we wanted to separate the sources. We wanted to find the separated sources, which are S1 and S2. So this is what we want to find. Is V sigma inverse U transpose X. However, also V and sigma inverse and U transpose are also unknown, and we need to calculate them. What is the interpretation of this SVD and this S hat equals V sigma inverse U transpose X? We are showing the interpretation in this figure. We start from here. The figure starts from here. We have S. do you remember x was AS, so was U sigma V transpose S. Therefore, first we start with this. The left side of figure is about this equation. The right side of figure is about this equation. So now let's start talking about the left side of figure. We start from S, then we want to generate X, the measurements. How? At first we multiply it by V transpose, then by sigma, then by U. Then we will have X. But what is V transpose, sigma, and U? V transpose, just assume that this shows the joint distribution of S1 and S2 somehow. So then if we multiply it by V transpose, we are rotating it, because if you remember in PCA we also had this. When you multiply by a projection matrix, if you don't truncate it, it's like a rotation. PCA was also like that. So when you say U transpose X or V transpose X, you are rotating X by the matrix U or V. Then V transpose, so you are rotating it. This is rotated as this. Then sigma scales it, because sigma was a diagonal matrix whose diagonals were singular values, and if you remember in PCA lecture we also said that there is a relation between singular value decomposition and eigenvalue decomposition. So it is just scaling this figure as we see here. With what values? With sigma 1 and sigma 2, with the diagonal elements of sigma. Then again we apply another rotation U, and we will have this. Therefore, this is the interpretation of SVD. It applies a rotation, it scales, and again it applies another rotation. Therefore, this figure becomes this. And this is the beauty of SVD. And then let's move back from X to S in order to estimate S by S hat. Okay, I need to fix my pen now. Okay, so we have this. Now focus on this equation, the second equation. We start with X, then we say we apply U transpose, you can see it here. Then we apply sigma inverse, you see it here. Then we apply V, we see it here. So we are doing this, and then we say we will estimate S. Here they are not, S1 and S2 are not completely statistically independent, but this approximation is good enough. Therefore, approximately they are statistically independent. And assume this, the angle of this is theta, the angle of this is phi. We will compute these theta and phi in later slides. Good. This is the interpretation of SVD and ICA. This figure shows it completely. So you need to understand this figure very well, because everything depends on this figure. Now let's go to step 1. So this is a step 1. This is a step 2, because the right hand side is what we are doing in ICA in this equation. So this is a step 2 and this is a step 3. Let's work on this. Step 1 on U transpose in this figure. See that? Okay. Recall we had this equation. So we are considering first U transpose X. Do you remember we assumed that PS1 and PS2 have 0 mean? Where did we make this assumption? In the slide in slide 6, item 1. We center the measurements x1 and x2. So we have this. Now let's minimize the second moment of or which is related to variance. Why? Because we want S1 and S2 to be very different from each other. Therefore, we should separate their moments. So we should make their moments different, and the variances of them should be minimized. Therefore, so all moments should be minimized. One moment is the moment of the moment of joint distribution should be minimized. The first moment was 0, assumed to be 0. The second moment or the variance we have here is a function of theta, and this shows the rotation of a matrix. So x1 and x2, we are summing over all, assume we have n samples of these measurements. For example, microphone 1 and microphone 2, each of which record n samples, n voices of these two groups or these two sources. So we have n samples of each, and then we sum over them. And then we also say that x1 and x2 cosine theta and sine theta. This is because of the rotation, and this can be written in this form: x1 cosine theta, and I think 1 squared here is missed. So we'll have x1j cosine theta, x2j sine theta, and then we will have so this, let's simplify this parenthesis. We will have x1 squared cosine squared, x2 squared sine squared plus 2x1 x2 sine cosine. So we will have this. Now let's take derivative of this variance with respect to theta. We want to find which theta minimizes that. Either if it minimizes or maximizes, it doesn't matter. It just we want to find its optimum. And then we say that, okay, what is the derivative of this term? It is this. The derivative of this term is this. The derivative of this term is this. The derivative of the first term is this, according to the definitions of sine and cosine and their derivatives. Then I'm repeating what we found here, what we found in the previous slide here, and then let's simplify this. We factor, so we are repeating this here while we said that cosine squared minus sine squared equals cosine 2 of the angle. We also have these two. We factor out sine cosine, and we know that 2 sine cosine equals sine 2 of angle, sine of angle multiplied by 2. We'll have this. Then we set it to 0 because we are optimizing. We want to find the optimum. Then we have sine of 2 angle, this, so we just take one of them to the other side of equation. We will have this equation. Then if we say that we just rearrange, sine of 2 angle over cosine of 2 angle is tangent of 2 angle, we'll have this. So theta is half tangent inverse or arctangent of this angle, of this angle. So theta is found in equation 8. We'll repeat it in this slide. So this is theta, and if we just represent it in polar coordinates, which is easier, we can say x1 is r cosine psi and x2 are r sine psi. Why do you do that? Because we assume that the measurements are also orthogonal. Then we say that if we put x1, replace it by its polar, and x2 by its polar representation, we will have r2 sine of 2 psi, r2 cosine of 2 psi in the denominator. Why? It's because sine cosine, 2 sine cosine is sine of angle multiplied by 2, and cosine squared minus sine squared is cosine to the angle multiplied by 2. So we can either have equation 8, 9 or 10 for theta. Now U as is a rotation matrix. Do you remember I said that U can be seen as a rotation matrix? This is the formula for rotation matrix in 2 dimensions. We can have extended to any number of dimensions. It has a formula. You can search it on Google. But this is for rotation in 2 dimensions, and if we replace this theta in this matrix, then we will have U. But what we want to recall this figure, we want U transpose in step 1. Therefore, we apply U transpose on this, and we will have this equation 12. So we found what we needed in step 1. After applying U transpose, we will have this shape. Now we are in this step. We need to apply sigma inverse. Step 2, sigma inverse. Do you remember sigma was a diagonal matrix with sigma 1 and sigma 2? What was sigma 1 and sigma 2? We showed this in this figure. We had sigma 1 and sigma 2. But when we are now currently we are on the right hand side of the figure, we need to estimate sigma 1 and sigma 2. We also have sigma inverse. Therefore, sigma inverse is as it is a diagonal matrix, its diagonal is inverse. So we'll have 1 over sigma 1, 1 over sigma 2, and then we can estimate this sigma inverse by 1 over rho 1, 1 over rho 2. What is rho 1 and rho 2? We are showing it in equations 16 and 17. So rho 1 is again summation over the n samples, and this is the rotation, x1 cosine plus x2 sine, which is squared. And this squared is because of the quadratic characteristic of variance, because we are showing the scaling or variance. And the rho 2 is just orthogonal, theta minus pi, half of pi. So the angle is minus half of pi, because we want rho 1 and rho 2 to be orthogonal. Why? Because also in this figure sigma 1 and sigma 2 are orthogonal. We want rho 1 and rho 2 to be orthogonal too. Then so we, according to equations 15, 16 and 17, step 2 is also done. But what is this? After this, if you I'm repeating the figure here, you can see that from this we have come to this, and this means that we are making the covariance equal in each different directions. In other words, we are making the covariance matrix the identity matrix. So after steps 1 and 2 we will have this. Do you remember this was S hat? So after the step 2 we are here, we have this. This is called whitening. You see it a lot in the ICA literature. After whitening, the covariance matrix becomes the identity matrix. As you can also see in this figure, it has become equal in different, the variance has become equal in different directions. And another figure is this. If you see, for example, this is the centered data, and notice this, it is centered 0, 0. Why? Because in slide, you remember in slide 6, item 1, we assumed that we are centering x1 and x2. So here we are the data is centered, and then we have applied this. This is exactly what we have in here, and then we have removed the rotation, and then we have this. So if you see, this has been removed, its rotation has been removed, and also its covariance matrix has become identity, and you can see this. Its covariance matrix so this is whitening. And if you see in each direction, this is 1. Sorry, this is not 1, but I'm saying that in what I mean is that this is equal to this, or these are equal. This is because of whitening, because of having identity matrix as a covariance matrix. And step 3, let's move on to step 3. What was the figure here? In step 3 we are talking about V. So after step 3 we will find the estimation of sources according to this equation, which is S hat is equal to V sigma inverse U transpose X. So now what should we do for step 3? Do you remember we assumed that the first moment is 0 according to our assumption. The second moment, which was related to variance, was also taken care of in step 1. This third moment is a skewness. However, we usually in natural images or natural data are not skewed. So we ignore that, but we take care of the fourth moment, which is more important in our case, in our application, and it is kurtosis. And what is kurtosis? I think you already know that in the course, but I review it. Kurtosis is a statistical measure which defines how heavily the tails of a distribution differ from the tails of a Gaussian distribution. And do you remember we also assumed that S1 and S2 do not have Gaussian distributions? In slide 6, bullet number 2, we said that they are not Gaussian. Intuitively I showed you why in this figure, in these two figures, I showed you why we don't assume they are Gaussian, but I said I will tell you the reason later. This is the reason we don't assume they are Gaussian distributions. Why? Because otherwise their kurtosis will be 0, and this step doesn't make any sense. So as we assume they are not Gaussian, they have kurtosis, and each of them. And the kurtosis, which is a function of phi, and what was phi? Phi was the angle for this. This was the phi. We sum over the n samples that we have in the measurements, and we have this because of the rotation. This is because of the formula of kurtosis, this power 4. We take derivative, we set it to 0. After some computations, we will see that phi is calculated as this, equation 19. If you compare equation 19, which is phi, with equation 10, which is theta, they're very similar with some differences. For example, 10 is not powered, the whole parenthesis of the tangent inverse. However, here we have in 19 we have 4 and 4 here. However, in 10 we have 2. This is one of the differences. We have several differences between phi and theta. So this is phi, and we again, as I said, V is also another rotation matrix, like what we had for U or U inverse. And V is according to the rotation matrix in 2 dimensions. We have this, but the angle is phi now. So this is now we have found V. Now let's move back to this figure. So the step 3 is done, and we approximately have the sources S1 and S2, which roughly they are statistically independent, and what we wanted to find are found. The sources are separated now using ICA, or singular value decomposition. Now let's show you some examples. The reason that I cannot show you the examples visually because usually ICA, for example, is used a lot in speech recognition, and you need to hear that. But you can see that, for example, it is used for music separation. You can go to this website and see that. Assume that you have two musics playing at the same time, but they are not very similar. If the two musics which are playing they are very, very similar, then we'll have a problem in separation. But assume they are a little different. For example, one of them is pop and one of them is rap, and they're playing at the same time, and you can separate them using ICA. Speech separation: if two people are talking, for example, you record them separately, but using a tool, a software, you just put the voices together at the same time, and then you give it to ICA. ICA can, with a good accuracy or approximation, can separate these two speeches. It is also used in medical applications, like for EEG separation. EEG is the signals of brain, and as I think you have seen it, they put some hats on the heads with some sensors on the sculpture, and they record different things from different channels, different signals, EEG signals from different channels. However, because they are very close to each other, these channels, they affect each other. Therefore, in order to separate the independent components in EEG signals, we can use ICA. They usually use ICA, and it's published in NeurIPS conference. We'll see that. It is also used for fMRI separation. fMRI is also interactive videos of brain activity, and they can also separate independent components in fMRI data. We can also learn some independent filters on natural images, if you go to this website, you'll see that they have learned some filters which are almost independent or statistically independent, and they have found that the learned filters by ICA are edge detectors, which is very interesting. So because the edge detectors are different edge detectors that they have found are detecting different edges in different kinds of edges in the image. And some useful resources to read. As I said, ICA can be done using singular value decomposition. There are 3 tutorial YouTube videos by Professor Jonathon Kutz. It's a playlist of 3 videos which cover ICA. The slides that I explained are based on his videos. There's also, we can do ICA using maximum likelihood estimation, and one good tutorial video on ICA using MLE or maximum likelihood estimation is by Professor Andrew Ng at Stanford University. You can see his YouTube video too. There is also a survey paper on independent component analysis. There's a tutorial paper on independent component analysis. There's another tutorial on ICA. There's a survey paper on ICA and its applications. There's also a book on ICA. These are the references. We have the first paper is ICA on EEG, published in NeurIPS conference, and there is also ICA on fMRI, and there is this The third paper is survey on ICA. The fourth is a tutorial on ICA. The fifth is another tutorial on ICA. The sixth reference is a survey on ICA and its applications. And the seventh is a book on ICA by MIT Press. Okay, I hope this was helpful and useful, and have fun. Thanks.